Welcome to the Design Principles and Firewall Use Cases video in the Cisco Secure Firewall in AWS video series. Hybrid Mesh Firewall is a new market category that focuses on unifying physical, virtual, cloud, and agent-based enforcement to simplify security operations. The intended audience is anyone who wants to better understand hybrid mesh firewall solutions. Also, network security practitioners who are looking to extend their skills into the cloud. Cloud practitioners want to understand how security solutions are implemented in a multi-cloud or hybrid cloud environment. And frankly, anyone who wants a better understanding of AWS and firewall deployment in the public cloud. The objective is to provide understanding of design considerations used when deploying security in AWS. The prerequisites are a basic understanding of network technology and network security, at least for physical networks. We also assume the knowledge presented in the fundamentals, architecture, and routing videos of this video series, or comparable AWS knowledge. We will discuss use cases and best practices, and then detail firewall placement in the public cloud. We then discuss microsegmentation and touch on management and attribute-based policy. This video focuses exclusively on Cisco security solution, the primary focus being on the Cisco Secure Firewall Threat Defense. For brevity, we will refer to this product as FTD, or FTDv if we want to emphasize the virtual form factor deployed in AWS. In the microsegmentation section, we will discuss Cisco Secure Workload, but only at a high level. And in the management section, we'll touch on Cisco Multi-Cloud Defense, but again, only at a high level. Let's move on to the discussion of use cases and best practices. Here is a list of the use cases that we will detail in this section. For ingress traffic, high availability and scaling for FTDv is generally provided by external network load balancers. This requires that you understand in advance the services that you will be allowing inbound traffic to. It requires source NAT on the FTDVs to guarantee that the traffic is returned to the proper FTDV. Combining the external load balancer with FTDv provides advanced NAT capabilities. This supports both distributed and centralized ingress. Instead, a gateway load balancer can be used. This has the advantage of handling all ports and protocols with a single front end, but it has limited NAT capabilities. You must use the public IPs of the back-end servers. FTDv and Gateway Load Balancer cannot perform NAT for inbound traffic. It only supports distributed ingress across your VPCs. A key consideration for egress traffic is what IP address will be used as the source of the egress traffic to the internet. Simplest would be to use the public IPs associated with the virtual machines. And this is what is done typically with a gateway load balancer implementation. You can instead use public IPs on the FTDVs as a source address for the egress traffic. This simplifies deployment, but it results in unpredictable outbound source addresses as the traffic is load balanced between multiple FTDs. This can be used with network load balancers or with gateway load balancers using a so-called two-arm deployment. Instead, you can have a NAT gateway. This provides a public IP to be utilized by multiple servers on private subnets. This can be integrated with network load balancers or with gateway load balancers. Since we did not discuss NAT gateways in the architecture or routing videos in this video series, we will provide details here for your reference. Note that we need both a gateway load balancer endpoint subnet and NAT gateway subnet to handle the routing within the application VPC. Here we provide the route tables for the three subnets: the application subnet, the gateway load balancer endpoint subnet, and the NAT gateway subnet. For east-west traffic, we could use network load balancers, But one of the challenges is that often for east-west traffic, you don't really know which services are going to be used by which devices. To allow all ports and protocols, you must use a gateway load balancer. To inspect east-west traffic, you may use a one-arm deployment of the FTDVs. In the one-arm deployment, no natting or routing is configured on the firewall. You could use a two-arm deployment. This allows you to combine east-west and egress traffic inspection in a single set of firewalls. In this case, FTDv must route the inbound traffic through the outside interface. FTDv will also perform source NAT on the traffic bound for the internet. When connecting on-prem data centers to the cloud, the locus of inspection depends upon the technology used for the connection. With Direct Connect, you can do the inspection either on-prem or in the cloud, but it's most often done on-prem with a physical or virtual FTD. If you're using AWS site-to-site VPN, again, you will typically deploy the FTD on-prem to take advantage of VNG dynamic routing. When using Cisco site-to-site VPN to connect to the cloud FTDv can be utilized. This unifies inspection across all cloud traffic. If you're using a transit gateway VPN attachment, typically you will prefer to do the inspection on-prem. This can significantly reduce bandwidth requirements, particularly if you're doing layer 3 and layer 4 inspection only. For remote access VPN, best practice is to use DNS load balancing. Solutions such as Route 53 are available that can balance traffic based on many attributes, including latency and geolocation. On the FTDVs, you use disjoint address pools. This allows you to distinguish the traffic within the AWS infrastructure and return the traffic to the correct FTDV using static routing. For site-to-site VPN, high availability is best provided by redundant tunnels. BGP is used for path selection. Failover time will only depend upon the BGP timers. However, within the AWS environment, you will have to do source NAT to guarantee that the traffic is returned to the correct FTDV. Let's look at firewall placement for a single VPC deployment. Traditionally, you used a so-called load balance sandwich. The internal load balancer, a network load balancer, was utilized for east-west and outbound traffic. However, this required that the services be specified. Inbound traffic typically used an external network load balancer. Gateway load balancers provide outbound, inbound, and east-west traffic for intra-VPC communication. Let's talk about firewall placement for a scalable number of VPCs. The focus will be on gateway load balancers. The gateway load balancer can exist in any VPC since private links will connect it to the gateway load balancer endpoints. One common configuration is to put gateway load balancer endpoints in each application VPC, but have them communicate to a single gateway load balancer for centralized inspection. For east-west inter-VPC communication, a transit gateway is required. Traffic is forwarded through the transit gateway to the service VPC, which is directed to a gateway load balancer endpoint. Here we see a topology that unifies ingress, egress, and east-west traffic in a centralized security model. We discussed this in the architecture video in this video series. If desired, you could actually combine these two sets of firewalls into a single set of firewalls. Since we're using a two-arm deployment for the gateway load balancer, we need to set up static routing on the FTD to distinguish the internet-bound traffic. Let's move on to micro-segmentation. Hybrid mesh firewall solutions are expected to perform macro-segmentation and micro-segmentation. Macro-segmentation is generally provided by Cisco Secure Firewall, whereas micro-segmentation is provided by products such as Cisco Secure Workload and Hypershield. Cisco Secure Workload provides micro-segmentation. Policy analysis is facilitated by visibility through multiple sources, either both agentless or agent-based. Once the policy is analyzed, it can be deployed and enforced through those agents or through agentless technology. A key capability of Cisco Secure Workload is the discovery of application dependencies. The application dependencies allow Cisco Secure Workload to design appropriate policies for microsegmentation. Cisco Secure Workload integrates with FTD. The FTD can generate information that details traffic on the network. That information is consumed by Cisco Secure Workload, which utilizes it to generate dynamic policies. Those policies can be deployed through an API from Cisco Secure Workload to the Firewall Management Center. The Management Center then deploys those policies to the FTDs. Cisco Secure Workload can also enforce the policies through both agent-based and agentless technology. Let's briefly discuss firewall management. Cisco Security Cloud Control unifies the management of multiple Cisco security products. This simplifies IT management, allows you to use unified policy constructs across multiple devices, can automate manual workflows, and can predict patterns with its AI Ops capabilities. Cisco Secure Firewalls are managed by Cisco Firewall Management Center, or FMC. This is a centralized management platform that provides sophisticated configuration, monitoring, and security forensics for our Cisco Secure Firewalls. FMC is available in multiple form factors. It can be an on-prem hardware or private cloud deployment. It can be a public cloud virtual machine, or a SaaS offering called Cloud FMC, delivered as a component of Cisco Security Cloud Control. You can also have hybrid deployments. For example, you may wish to do the configuration from the cloud, but keep your events and security analytics on-prem. On-prem FMCs can manage AWS FTDVs. Matter of fact, this is quite a common deployment. This can be done through a VPN, through the internet using public IPs on your FTDVs, or through Direct Connect. FTD orchestration in the public cloud is provided by Cisco Multi-Cloud Defense. There are three wizards that are illustrative of the workflow. First, you must connect your accounts to Multi-Cloud Defense. These could be AWS, Azure, OCI, or GCP accounts. Once the accounts are connected, you get a unified inventory across all of your public cloud accounts. The next step is to enable traffic visibility to see what's happening in your public clouds. Cisco Multi-Cloud Defense utilizes cloud-native constructs to enable traffic visibility. In AWS, these are flow logs and DNS query logs. Thus, the administrator is insulated from the complexity of configuring these visibility tools. The last step is to deploy FTDVs in your cloud environments. Cisco Multi-Cloud Defense supports both centralized and distributed security models. For centralized security, it will automatically deploy the transit gateway, create all the transit gateway attachments, and configure the routing to direct the traffic to the service VPC for inspection. For distributed security models, FTDVs are deployed within each individual VPC. You can combine these models using a distributed model for some VPCs and a centralized model for others. Let's conclude with a discussion of attribute-based policies. Cisco Secure Dynamic Attribute Connector, or CS Stack, provides metadata required for attribute-based policy configuration. Of particular interest are the AWS and Multi-Cloud Defense Cloud Connectors that give you the tags of the virtual machines. If you're using the AWS connectors, you have to have a separate connector for each AWS account. However, if you have multi-cloud defense, you can unify that information across all of your AWS accounts with a single connector. Let's look at the architecture of CS Stack. CSDAC is provided either as a built-in component of the FMC, as a SaaS service integrated with Cisco Security Cloud, or as a standalone virtual machine. It gathers information from a wide variety of sources using what are called connectors. It processes that information in what are called dynamic attribute filters. These allow you to use Boolean logic to construct meaningful attributes from the raw attributes generated by the connectors. Those attributes are then communicated to the FMC, which can dynamically update the policies on the firewalls, thus providing dynamic, attribute-based security policy. Thank you very much for your time.